Hi guys, this video today is going to be on piecewise and step functions, and we have started to learn a little bit about piecewise functions from the journey to the bus stop problems that we've been doing. Take a minute to write down, also, this page is probably at the beginning of your packet. I believe it's on page 3. So flip through your packet, find page 3, I think it's page 3, and find this page, and that's where we're going to be taking notes today. Okay, a couple of definitions. A piecewise function is a combination of one or more functions. It has different rules for different domains. And that is what we did with our journey to the bus stop problems. That is, we had different functions all put together, and each one took place in a different area of the x-axis. Another type of piecewise, a specific type of piecewise, is called a step function. So a step function is a piecewise that is constant for each interval of the domain. And so I think if you look at this picture, this is an example of a step function. And can you see how it's like there's different steps at each place? That's why it's called a step function. Take a minute to look at this and kind of try to make some sense of it and try to figure out what is going on in this graph. So you're going to look at the y-axis and what's happening, look at the x-axis and what's happening. Can you read this graph? Do you know what it means? So what's happening is we have different fees for different times. And that's what a step function or a piecewise function does, is at each different time along the way, there's a different rule, a different function. And so, again, back to our journey at the bus stop, like there was a certain time when they were walking, a certain time when they were hurrying, a certain time when they were pausing, and all of that ties back to a piecewise function. Let's take a minute to look at these equations, and we've been looking at these with our bus stop, so you guys are familiar with this. There are 3 equations here. What are those 3 equations? Take a second to pause it here and write down those 3 equations. Okay, you should have y equals 27, y equals 24, and y equals 12. Because they're horizontal lines, it's just a plain old number. That's all we have. Okay, to create a piecewise function, what we do is we're going to erase those y's, and instead of having all those different ones, we're just going to say that f of x is equal to this whole thing. But we know it's not always any one of these. Each one of them has like a certain parameters that they act within. So when it's in between 8 o'clock and noon, it's 27. And we've been working with interval notation, but on this one, I'm going to go ahead and use the inequality notation. So this says when the time is between 8 and 12, the cost is $27. But if the time is between noon and 4, then it is $24. Now, let me just talk a little bit about that. It doesn't seem to make sense because it's like counting up to noon, and then the way we do time is then we start off at 1 again. So numerically, 12 is less than or equal to x is less than 4. It doesn't make a whole lot of sense, but if we did military time, it would. But let's just not even get into that, and let's just leave it as 4. Notice also I put a equal to because it's basically it includes that one. And I put the equal to here because it includes that one. And I put an in less than without the equals because it's an open dot. And then the $12 is if you show up between 4 and 8, then it's going to cost you $12. So this is a step function, also a piecewise function, because at each place there's a different cost. Here's your time, here's your cost. There are a lot of instances, real-world instances of step functions. I think step functions might be more realistic than just a basic linear or a basic quadratic or whatever, because in step functions we look at the difference and how much is each one changing by, like, you know, what's happening at this time, what's happening at this time, and so forth. So whether you're talking about distance traveled, like the bus stop problem, or maybe you're talking in chemistry about whether it's, you know, is it a liquid or is it a solid, that kind of thing. All of these things could be represented by step functions. or excuse me, all of these things could be represented by piecewise functions. Now, a couple of skills that we need to be familiar with. We need to know how to evaluate a piecewise function. So that's what we're going to talk about here. Notice, here's my piecewise. I've got some rules, and I've got when it's going to be each one. And it's asking me to find g of -5 and g of 6. Let's start off with g of -5. The first step is to look and decide, should I use the top equation or should I use the bottom equation? Well, the way you decide that is you look at this part on the right-hand side where it says if x is less than 5, use this one. If it's greater than or equal to 5, use that one. Well, it's less than 5, so I'm going to use the top equation. And I'm going to go ahead and plug in that -5 in for x. So I'm going to take that -5 from the problem, plug it in here, and work it out. And so when I work this out, I get a -11 as an answer. So that's just saying that g of -5 is equal to -11. Okay, the next question asks, what is g of 6? So if we go up here, 6 is greater than 5, so we ought to use this bottom equation. So we're going to plug in a 6 and work this one out. And so after I work it out, I come up to that g of 6 is equal to 33. So this concept is something you need to know how to do, is how do you take a certain number and decide where to plug it in, and then you just work it out. Okay, what about graphing? I'm going to cover graphing using a table of values. So I have two parts of my graph. Each one has a different domain rule. I'm going to make one table of values for the top graph, and I'm going to make a different table of values for the bottom graph. Now, what numbers to put in? Well, notice the top one says anytime x is less than 2. So if it says 2 here, I'm going to start my table at 2. But it says less than 2. So I'm going to go down from there. I'm going to say 1, 0, and maybe -1. You need to have at least 3, but 4 or 5 is probably better. Okay, another thing is this was a less than, so we need to remember that that's going to be an open dot. Remember that an open dot is for less than or greater than, but a solid dot is for less than, equal to, or greater than equal to. Okay, so if I plug these in, I'm going to plug in my 2, it gives me -6, plug in my 1, plug in my 0, and finally my -1. Okay, now I'm going to go to my bottom one. It also starts at 2, but this one says greater than. In fact, it says greater than equal to, so I'm going to have a solid dot on that. Greater than equal to, so it's going to go to 2, 3, 4, 5, and so forth. Okay, so let's plug these numbers in. We take a 2, we plug it in. We take a 3, plug it in, and so forth. All right, let's get to graphing now. I'm going to graph these points, 2, -6. Now, 2, -6 should have an open circle because that was less than, not equal to. But the rest of them are included, so 1, -3, 0, 0, -1, +3. So this has a slope of 3. You can see that from the original equation. There's a slope of 3. And I need to move that point over. So we're going up 3, left 1, up 3, left 1, etc., because it's a -3. Now when I connect my points, I'm going to connect them with an arrow. So this is my function for f of x is -3x. It's always in the less than 2 on the domain. Okay, let's talk about the other line. The other line starts at 2, 5, and this time it has a solid dot because it's equal to, and then 3, 6, etc., etc. This time we have a slope of 1, and so again, when I connect these, it's going to look like this. I have a solid dot, I have a slope of 1, and it's going forever in this direction. I also want to talk a little bit more about graphing. That this graph, the red one, had a y-intercept. It has a y-intercept of 0. The bottom line also has a y-intercept. It has a y-intercept of 3. We just didn't include it on our picture. Like if we kept going back with a slope of 1, it would hit there at 3, which was the y-intercept. But this is where we were talking about a little bit in our bus stop problem is that's not going to exist because at this point, at 2, we start doing something else, okay? So it'll have these breaks in it. Not always, it depends on how the graph looks, but sometimes there will be these breaks in the graph. The next thing I want to talk about here is how to evaluate. So we have f of -1. And so if we go to our graph and we go to -1, we come up here and it hits -1 at 3. That's one way we can evaluate. Just look at the graph and see where it goes. Another way we can evaluate is we can go to the table and we already plugged in a -1 and we got a 3. Or we can go up to the equations and decide which one to use. -1 is less than 2, so we're going to use this one, and we plug that in, we would get 3. Let's do the same thing for f of 4. If we go to the graph, here's 4. I go up here, it looks like it's hitting there at about 7. So f of 4 is 7. Another way to do that would be the equation. 4 is greater than 2, so if I plug in a 4, I get 4 plus 3. Or we also do have it on our table, 4, 7 goes together here. So any one of those 3 options. We will continue to work with piecewise functions in class. We'll do some warm-ups on it and some problems with it so that you can really understand it. But if you have questions, please write down any questions so that when you come to class, you can ask questions. Also, a summary. Let me mention about a summary. If there's no lines here for the summary, then you don't really have to write a summary. But getting in the habit of writing a summary is a good habit to be in. So you might just want to do that just so that you have it and you can come back and look at it. But that is not a required part. That will just be extra on your own. Okay, that is all for the video today, and we will talk about this more in class tomorrow.